and just the simplest version of something that you could find. Let's say you had a pump. Oops. Let's say you had just a pump here. So you had this pump, and I'm going to draw it like a circuit. Okay, so here's your pump. Positive pressure, negative pressure. It draws out here. So if you look at it, let's just say this, the losses here, FL over D, I'll say equivalent, just the equivalent length, V squared over 2G. And if you look at this thing and you pick a spot and you call it 1, and you pick the one right next to it, call it 2, P1 over gamma plus Z1 plus V1 squared over 2G minus all the losses plus the head of the pump is equal to P1 over gamma plus Z1 plus V1 squared over 2G, because you went around the loop all the way back, which means you're left with that. Head of the pump is equal to F L over D squared over 2G. Now let's say you were in the flat region of Moody's diagram. So it became flat right here. So this means, and you assume you're up above here, so you have a fixed Reynolds number. However, over here you have a pump. Now what they do a lot of times is they say we want to do an equation. And so they'll look over here and they'll take this thing and then they'll say, okay, head of the pump and Q. Or you could strike that and say velocity. Now if you look at this thing and try to fit that to a curve, H is equal to, what you'll find out is, let's call it H1, which would be this location right here, H1, minus some constant times Q squared, or if you're, another way of doing it is some other constant times V squared, where the only difference is, you're looking at, how you get, this is how you go from one constant to the other. So if you look at it from that standpoint, you say, well, this is going to be the head of the pump. So there's your head of the pump. It's just an equation. It's quadratic. It sort of comes across and dies off. And you'll notice most pump curves look that way. So in the real world, what you have is you have H1 minus C2 V squared, which is from this equation. If you copy this down, and then you head down here, let's see, I'll put it right here, and then I'll move it. So if you're looking at this, in other words, what I'm saying is these are the same things. This is the equation, this is the pump curve. And here's FL over D, V squared over 2G. What's interesting is this is a case in which the real world is easier than the textbook world. Because in the problem you had to take home, he had this thing in some sort of backwards way presented to you. Look at what you have here. On the right side, you have a term in which everything is a constant. It could be written as C3V squared. On the left side, you had this. And so all you do is you move that junk over to here, and you have what is essentially H1 is equal to C2 plus C3 V squared. Part of that being the drop, the pressure drop, part of it being from the curve. And so just like that, you take something that's a real world problem and you realize you end up, well, I didn't have to put that over. You end up with something like that where C3 is nothing more than, here, let me see if I can put it in. F L over D 1 over 2G, which is the part right here, this part right there. And then the C2 came from data from a curve. So you may see this on the file. You may see a pump that sat there. and I drew it out. And now I drew it by hand. Well, okay. You go and you look, okay, you can find the pump curves that don't exactly behave this way. They don't drop in Q as a Q squared. But the question is, if you're sitting at your desk in the real world and you've got something that's slightly shifted, say, here is what it would look like if I said 50 minus 2.3 v squared, and here's what it looks like if it's the real pump curve. So what? Doesn't really matter. So if you're down around in here, yeah, you probably shouldn't even buy that pump to begin with. If you're up and around in here, that's probably where you want to operate in anyway. And is the difference that much? Well, it's, if I want to fit it exactly and then go do it, have at it. But you'll be sitting at your desk 8 hours, and I'll be taking a 2-hour lunch at Quiznos. And so, and then driving back the long way by the lake and looking at it while you're still at your desk, trying to fit this curve to the nth degree and find out your answer didn't matter that much different than mine anyway. So the key is when you look at it, this is the real world kind of situation. I'll probably give you a pump curve, and you can sit there and work real hard on it. You can just sort of straighten and say, well, I think this is dropping. One of the ways you can do it is if somebody gave it to you and said, this is 50. We went over here to say, you know, and it may end up, you know, where it's this way, you know, 5 cubic feet per second. So in other words, this is Q out here. Oops, that doesn't look like a 5. And then the other thing is maybe drops. This maybe is 45, and maybe this is, you know, 35 and 7. Then you can kind of get an idea. One of the things you can do is if I know this is 50, if this is where the intercept is, and that head of the pump is equal to 50 minus some constant times Q squared. Well, if I want to find that out, well, if the head of the pump is 45 equals to 50 minus C times, grab that, 5 squared, all of a sudden you've got the constant. You move, I don't know which one you want to move. You can move that one over, and that would be C times 25, and then move this one back over, and the difference there would be 5, or the C would be 5 over 25, which is 1/5. Is that right? So just like that, you have your C. So your pump curve out of this would be nothing more than head of the pump would be 50 minus 1/5 of Q squared, just like that. And so, yeah, you might find that over here, if you did 35 and 7, it might be a little bit different. You know, I've seen people do it and list a couple of them out and get the constant and just average them. And say, well, one is 1/5, one is 1/6, and one is 1/4. Add the average. Let's just average it. Let's go with it. And so, you know, those are type things that you do and when you're out there, because you just want to get a rough estimate if you even should buy the pump. And then if you say, well, I shouldn't even buy this pump, guess what? You go look at another one, you pull it out of Grainger's catalog, you're doing it again. So you want to do that and spend 7 days doing it, picking 7 different pumps, or just go in and say, well, let's get a rough estimate. Am I even close to the flow rate I need? And by the way, if you do that, you can find here. I don't know if I can spell Grainger's MSC.com. I know I can spell MSC. Oh, is it? Oh, okay. Well, then Grainger's. Did I go to the wrong site? Grainger's. So yeah. So if you go in here, you can look for a pump. Water. Let's just do water pump. Oh, give me a break. What? No thanks. We're sorry, you cannot complete. Well, let's just find pump then. What you'll find in a lot of these centrifugal pumps, just pick a pump, any pump, just here. And then, good grief. I mean, we're getting down to the point where we're, okay. So here is phase, I don't know. Here, I don't care. Let's just pick a pump, view product details, what you'll find in Granger's a lot of times is this. Now, there, you can go to the manufacturer and get the PDF to look at what he's done. Gallons per minute at 20 psi, gallons per minute at 25, gallons per minute at 30. From these, just the 1, 2, 3, 4, 5 of them, you can pull, or, yeah, you can pull, you can make your pump for it. So that gives you an idea. You can just rough estimate, kind of get an idea of what it is. Go find out if you want to pay $529. Yeah, $529. Now that's not a terribly expensive one. You can find these things $2,000, $3,000, $4,000 pretty easily. We have ones about like this downstairs. We were building a circuit. We just never got done with it. So you can do stuff like that. You could probably also find, I bet you, oh no, this is not the this is the $621. So look, you can zoom in somewhere down here. They may be able to, I know MSC used to be able, this was years ago, used to be able to get the actual brochure from the manufacturer. But I don't see, do you see a link? Help us improve our technical. Look, they need my help. I mean, come on. I need help. Was there? Oh, right there. How can we improve our technical specs? Okay, so I don't see. Oh, it comes from India. Well, they're view the product. Let's see. The booster pumps. So anyway, somehow, yeah, it's in there somewhere. I'm just not sure how to get to it. Okay, now I'm looking at the $500 pump. Oh, operating at parts, man. No, that's a parts. That is probably not. Let's see if they might have the pump curve in there though. Well, they kind of do. Gallons per minute at pressure boost in PSI. Okay, that's not. Oh, and I guess maximum. Okay, I don't know. They should just supply a pump curve. Most of them do. So I guess these guys they're telling you how to tear it apart. Yeah. So you can construct those from this. Usually you don't have to do that. Okay, so if you go out and just did, what you'll find is how to read a pump curve. That's not, so here's what you can do. Images, and then you can find pumps and systems. Then you can go to their website, and then, go away. A lot of times you'll find the pump curve is for a specific pump, but I don't see that there either. You can kind of tell the ones that are somewhat efficient. So here's another thing. Might as well look at this. Oh. Okay, come on. Why is it doing this? So, no, I guess it won't. Anyway, one of the things about these pump curves is there's an efficiency contour map in there. So it's 40% efficient operating back here. So you kind of want to operate as much as you can right around your tube because it's more efficient. Well, if that's the case, then go ahead and pick this point to find the constant, make it cubic. I mean, quadratic, drop off like this. Because you don't want to be back here or over here anyway. So you kind of want to be, that's 60, I think that's 70. I would say I would try to confine myself around it here. If I'm doing that, I bet that looks probably like it's a pretty good place to pick off, just pick the spot off and find that constant. Run the calculation, figure out if you only want to buy it. And For that matter, this one has, how many diameters? It's got 5.5. It's got a whole bunch of diameters. So I would go down here and pick these and pick off the curves all down in here. Just draw lines with the constants for each one of these. Take the supply head back here, and that gives you enough to go up, calculate and go up down the chart and figure out which one of these you want to buy. So, and of course, price goes up as you go up the curve. So I'll give you something like that. I may even actually go try to find a real pump curve if I have the inclination, because I'll probably use this surface, turn it sideways, and make the test on it. So be expecting, multicolors too. So that means if you need it printed in color, just let me know. If you want it in color, let me know. I'll get it printed downstairs and put it in my box. So if you just say, I don't have a color printer, but I really want to work it in color, you can go buy the box down there and pick up your color version. Anybody want it in color? Oh, you do? Okay. I'll email it to Carla and tell her to print, like 25 copies and put in my box. And, and that means you can work at home, but I'd like you to work it on that page. So don't work it on a other sheet of paper. No, just work it on that sheet of paper. I'll go ahead and get some colored copies made so that color can actually wake you up while you're sleeping. You ever watch like some of the kids programs? PBS, these kids, like somebody's in an Amatron outfit and they're, I'm talking about for 3-year-olds. You ever notice how they're always primary color? So this works with adults too, because I've sat there and watched those programs before and thought, man, this is really colorful world here. Just, and they're always like, here's a bright blue character, bright yellow character, and they're dancing around doing stuff.
You do circuit or using statics and colored pencil. Anytime you ever do a resistor and changing voltages and all that, change the color.
Oh, there you go.
When you go, if you have something that's complex, now you have to go back and get something.
Actually, aren't resistors color coded anyway?
Yeah.
So see, they even knew that. Okay, so I'll send you an email later. I'll go ahead and post it. But for real, do you want it in color? I mean, I'll send it down there. Okay, I'll send it down there. Some of you say no, so there's like 30. So what I'll do is I'll send her the file too. And so, I'll say print out 10 copies, put it in the box. When those are exhausted, another 10, do it that way. So in case you guys do want it, it could help actually, because if there's a lot of drawing parts that I come up with,
I wanted to ask her some of the I get that basically 50 is the H1.
Yeah.
The H1 is our 50. And then here you basically said that HP is 45.
Yeah, so what I was doing, I was picking a spot right on the curve, and if it comes over and say, well, that's 45. So the head of operating there is 45. And this is directly brought down because it's the intercept. And then this is the 5. So this is the flow rate here. So I'm pulling it off.
That's a 5. Okay.
Yeah.
I was trying to figure out where on earth a 3 was coming from.
Oh, I'm sorry. That's a 5. Okay. Okay. That's a 5. Okay.
That's where I was getting confused. Okay.
Okay. Yeah. And that's a 5 too. So yeah.
And then we can just kind of solve this for the C.
Yeah.
And then what do we do with the C?
Then what we have is we have this. Okay. So when we have this, then let's say, okay, so when we have this is an actual pump of the thing. And the equation, well, let's go back to right here. So what we have here now is 50. What did I say? 1/5? And let's say it was V squared is equal to, and let's say F L over D V squared over 2G. Let's say all these terms end up being 100. So we had 100, this 1/5 V squared 50. All I do now is I have an equation which I can solve for V squared, or solve for V, sorry. And I
Okay,
get
I
it.
see. And this F is what we get off the Moody chart, right?
Right.
The L is the length of the pipe, the
Right,
D is
D
the diameter of the
diameter,
pipe, 2G
2G,
is just
yeah.
2G based on whether we're
Yeah.
English or standard.
Yeah, and that's
Okay.
it. Now, these are kind of an oddball thing because I put 100 here and then 1/5 there. That's not good. So maybe this is more along the lines of, instead of 100, maybe it's 1.5. Then it makes it more reasonable.
Right.
So, because then you take 1/5 and add to that, move it over, divide it out. So then you got 50 divided by what? 1.5 plus, what is that? 0.2?
Let's see if we
1/5. Move that
plus
over.
1/5, that's 1.7. Because 1/5 is 0.2.
Oh, okay, yeah. So I
Okay,
got,
we end up with
yeah,
1.7 V
okay,
squared.
yeah. 1.7, oops. 0.7 under there, end up with that.
Okay.
So that's all you're doing.
All
What
right, I
you're
was trying to
doing.
figure out where on earth a 3 was coming from.
Oh, okay, that's bad. That's bad handwriting.
Okay.
So all you're doing in that pump curve is trying to find those. Once you find those, then you're over here.
So we go to
And
a
then-
pump curve, we find a C.
Yeah.
Now, as far as like picking our second point on that curve, do we just grab anywhere?
Well, that's
Or
what I
do
was.
we go down to find like, here's a Q more, here's basically like the Q that we're looking, if we know the Q, right?
Yeah, see here, that's what I was saying. I was saying when you're looking at a real pump curve and you're like, well, if I pick a point right here, it's going to be really touchy. So I got to move out here somewhere reasonable. And there's those contour functions. Remember those?
Yeah.
So might as
I
well.
remember that they exist.
Yeah, so maybe somewhere around the highest efficiency, kind of get that idea. Pick that
Okay.
spot.
So
And then-
basically, we just kind of grab the high efficiency, assuming the pump map actually has its efficiency range.
Yeah.
Just grab something in the middle of the
Yeah,
efficiency
and
range.
just estimate it there. And
So
go
the
with it.
Q we grab here for this equation has no bearing on the Q we actually need.
Right, exactly.
Okay.
No bearing. It's
That's what I
just,
was trying to figure out.
yeah,
Okay,
it's
so we
just-
grab that.
it's just
understand the
getting
pump.
this curve. That's
Okay.
all it's doing. Then when you get all done, you could graph it. You could say, well, here's the actual pump curve, here's the other thing, and that's where it's going to operate. Now this Q is the operating point. You may have picked this Q
To
to
find
the
our C
thing.
value?
Right, and this one would be the operating point,
Okay.
and that's what you're going to end up with.
And this curve comes from,
This curve comes from F L over D, L over D, V squared over 2G. And so this could be V, and this could be like head. And so what you find out is this is just some constant times
Right.
V squared. So it's kind of parabolic looking.
right.
And this one's kind of inverted parabolic looking. And
Right.
so,
And across here, this is just our, this is our V in this
yeah,
case?
V, yeah.
Okay.
It could be either velocity
V
or Q, depending on which
Okay.
one is given. So, and I may give a Q on, because Q is more natural on pump curves.
Right.
So, but then you just, Q is equal to AV. You can solve it in Q or you could solve it in V, either one you wanted to do.
Okay. And if it's not too much to like grab one if you've got one, how do you read the Moody chart? I'm
Oh.
still trying to kind of.
Okay, so here's the way you read. I think I had it
I'm
in
trying to
here.
put together like all of the pieces from 4
Yeah.
6, and
Okay, wait a minute. I
can I
had,
still come by your office at 2:00 today?
yeah, I got to go to the physics lab at 2, maybe a little bit after that.
So what, like 2:30 or 2:45 or
Well, see, I got to leave at 2:45, so maybe 2:15.
2:15?
Yeah.
Okay.
Okay. Where is I had the I had the Moody. Here it is.
Okay.
So what you're doing with it is you're coming in.
I know
Let's
that
say
basically I'm supposed to end up with an F number. at the
Right.
end of it, right.
so. What you do is you'll be given somehow this E over D.
I'm given E over D, and
Yeah.
the D is the diameter of
Diameter,
my pipe,
yeah.
and that E is, or that
Roughness.
epsilon rather.
Yeah, epsilon
Okay.
is a roughness.
That's a roughness factor. Okay.
Yeah. Now this you'll have to calculate. So once you calculate the Reynolds number,
And that's rho times
Velocity,
velocity times
diameter,
diameter over,
mu,
and the mu is
the viscosity
the
of the
viscosity
fluid.
of the fluid. Okay.
So let's say you ended up with 6 times 10 to the 5th. And let's say your pipe, you ended up with this pipe.
Okay.
So what you do is you just go vertical until you hit that curve. And when you hit that curve, you head off to the left, straight or straight to
Straight
the left,
horizontal.
yeah. And then when you
Okay.
get here, this is the value.
Okay, I read an F, and then I plug the F into the H equals F times L over D times
Yeah,
V squared
right.
over 2G,
Yeah,
and that gives me my loss.
yeah, that'll give you your loss.
Okay, got it. Now, what was the H with the loss on the elbows and everything? How was that?
Oh, now that didn't even need a table. That just, the loss there was KL V squared over 2G. And that's just a flat number.
Okay, so
So-
KL is some number. I'd be given that in the
Yeah,
beginning, probably.
yeah,
Okay.
yeah. And that's it.
Or I'd be given everything else and told to find that. I
Yeah,
presume that could
possibly,
be a
yeah,
thing. Like you could
yeah.
give me this much is happening
Right.
around, some, and that would be like the KL of like the 90-degree elbows or
Yeah,
the
yeah,
joint in the other.
Right.
Okay.
yeah. So,
All right.
probably, yeah, I will do it somewhat that way.
Okay. All right. And the thing I'm basically going to come by around today is I realize that this is well past, but I'm still a bit of trouble figuring out the X component, Y component, the N factor and
Oh, okay.
positive and negative. And
Okay.
then how do I translate that positive and negative into a direction of the effective force because like when you've got
Oh,
the
okay.
problem where it's like, okay, this is going in this way. If the water's flowing this way, the normal is outward, so that end should be negative,
Right.
right? If it's
Yeah.
flowing into the pipe,
Yeah.
then if it's flowing out of the pipe, it should be positive.
Right.
But then if there's a bend in the pipe so that it's going in this direction and then coming out in basically that direction.
Yeah. Now, see if that's the case, what you find out, let's say, so something like
That-
this.
exactly that.
so-
You know the problem. I'm
yeah.
still trying to understand. Like
So-
you even showed me the solution to the problem, but I'm trying to understand that solution.
Okay, so this is say N2, this is say N1, this is say V1, and this is say V2. So in essence, since they're going together, V1, well, okay, so this is V2 dotted with N2. Okay, well, here, let me take this out. Is equal to just the magnitude of V2 times the cosine in this case is 0. So it just becomes equal to plus V2.
Okay.
So the magnitude
And that's V2
into,
in that direction.
yeah,
Now, is
straight
that
out.
a force? That's the velocity of the water coming out of it.
Yeah. So
Right.
let's say this one, let's
What
say
I'm
the
trying to say, how do I
pipe.
turn that into the force acting on the pipe is what I'm trying to
Okay.
figure out.
Now there's where you do, say you're doing some of the forces in the X.
Right.
Some over the control surfaces of Vx times, and I'll separate them, V dot N times area. So here's your key with
And is that a row or a pressure?
it's a row.
Okay. it's a row.
So it's the same thing as if you look at it, that's like M dot rho AV.
Okay.
And so the key here with this one becomes this. Let's say, let's say this happens to be 45 degrees. Now, if that happens to be 45 degrees, what you have to realize is V2x is equal to minus velocity 2 over square root of 2, because square root of 2 is cosine.
Are we
of it.
assuming X positive is that way?
Right.
Okay.
Exactly. So what you're looking at is this has a component that is associated with the coordinate. The V dot N doesn't. It doesn't matter what the coordinate system is.
Okay.
This just ends up being the M dot in this case flowing out is positive. So that's all it is. If someone were to tell you M dot 1 is equal to 5, then you'd say, hey, wait a minute.
M dot 2 has to equal to
5. And so this one becomes minus 5, and this one becomes plus 5. I'm sorry, this one becomes plus 5, and this one's minus 5.
We count out as positive.
Right, out is positive.
Okay, so out is positive, in is negative.
Yeah,
Okay. Now, if I translate this velocity into the force on the pipe,
now
like
see,
if I'm trying to
okay,
put this pipe in static equilibrium,
okay. So if you're trying to do that, what you do is if someone gave you, okay, so let's look at the left-hand side of the equation.
Mhm.
Let me redraw it. So let's say some of the forces in the X. The left side of the equation, say, looks like this, okay? It's sitting there, and now you have P1A1, and let's just say P2A2. Now, I don't know what those are, but here, let me move this. So now
now
I'm just,
water is still coming in here and out here.
right.
Okay.
So let's say I'm only looking at the X. Now, if I just look at this, it's a free body diagram, and somebody says I'm putting an FX on it, and then I'm going to put an FY. Now, right now, we're only dealing with X, so there is no. So what you realize, you say, okay, there's surface forces and body forces. If somebody told you the volume of this thing, then you could do it. Let's say, and gravity was going this way. But if gravity is going that way, that doesn't give you an X component. That just tells you, okay, it's gravity is pulling it down this way.
Right.
So it doesn't matter. But what it does matter is that you have a P1A1 moving to the right. You have a P2, whoops, a P2A2 here, but there's only a portion of it pushing to the right.
That's times cosine of whatever angle.
Right. And then the only thing you got left is FX. And that's it.
But here's where I'm kind of confused.
Okay.
If water's coming in here and out here,
Right.
all right, the water moving into here is pushing it that way, correct?
Right.
And the water moving out here is pushing it that way.
Well, okay, so.
The water exiting here pushes. So,
Well, here's the thing. Okay, so think about it like this.
does water entering push in the same direction that it's flowing, and water exiting push in the opposite direction that it's flowing? I
Well,
mean, that makes sense for as far as thrust and such goes.
well, see, maybe you need to work it and then think about it after you work it, because there are certain cases in which it could do the reverse of what you think. For example, let's say you had a pipe and it did like this. Okay, so the flow rate is really high coming out of there,
Right.
a lot higher than back here. So this one doesn't have as much effect as this one does. So that would push it forward and require more. Now you could have the reverse in that it would come in and then sort of dribble out. And then you'd have a really high one there. It's kind of dependent upon the problem.
I think that I'm not talking about the total direction. I mean, what do I do to determine this is the force entering, right? This is the water that's coming in, right?
Well, now see, this is just PA, and so he may
Right.
put a pressure. You know, he may say 10. Here it's 100 psi.
Right.
So you just say, okay, it's 100
Multiply
psi.
the
And
pressure
you just
times the area.
and you got that.
Right.
And then say over here he says, oh, it's 10 psi.
and pressure
then-
times area becomes a force.
Right.
Right. And what I mean is that this P1, that is the force that calculates the force on the assembly that is pushing this way from the water coming into the pipe.
Yeah. And then there's this one.
And that's
And
the
then there's
force
that
from the
one.
water. That's the force on the pipe that results from the water coming out of the pipe.
Right.
Correct?
Yeah.
What I am trying to figure out is how do I tell whether that's positive or negative?
Oh, okay.
That's what I'm trying to
Okay,
figure
so
out.
here's the way to do this. Okay, as I always put them as going in. Okay, P1A1, and I'll tell you why. Because there are cases in which it could pull a vacuum. If it pulls a vacuum, P2 may become -5. If it became -5, just carry it as -5. It flips the vector around. And so this is kind of like the inverse of the normal. If you just make it always go in, then it always works out. And so you can make this the gauge pressures. P is equal to gauge pressures. And then it always works. I mean, so you never have to really think if you make the vectors kind of push into the thing. And that's essentially it. That's all there is to it. So if you just carry that in a systematic way, then you're setting this part equal to this part.
Okay.
And then you just carry out the calculations and work it all done, and it works out, you know.
All right. Now, I'm trying to. You're saying sometimes this PA could turn out negative.
And if it does, just
Okay.
always draw it in, and when you put it in the equation, it turns into be a negative number because it's a negative pressure. So I always draw the free body diagram exactly like this and allow the pressures to tell me what do I put in this equation. So this drawing yields this equation. This is something separate. This is something that I'm not even going to consider until somebody tells me what number to put in there. So now somebody tells me, oh, well, for 2, I got to put in a -5 right there. But the correlation between the equation and the free body diagram is always the same to me.
May I draw something up on the-
Yeah, go ahead.
See if I follow on. I just want to make sure that I follow on. So, all right. If what I'm given is that I have water flowing in here
Mm-hmm.
and water flowing out here,
Mm-hmm.
and my N is this.
Uh-huh.
That's my N1,
Mm-hmm.
and then that's my N2.
Mm-hmm.
Okay? So, and here it tells me that T equals 10.
Mm-hmm.
Now, if over here it tells me that T equals X narrow velocity for high velocity, lower pressure probably. So let's call it 2.
Okay.
Yeah. First of all, am I following that this is narrow, so this should be at a higher velocity, so this should be at a lower pressure.
Yeah, and it could be even worse than what you think, because it could be some losses in there.
Yeah, like there would be in reality there would be a KL factor here to that bend. And
Yeah.
there would be the HL from the friction of the pipe and such. But if we neglect that,
Mm-hmm.
okay, so then I have, this area, let's just say this area equals 5, and this area equals 1. Just for the sake of things. So basically, I would then take P1A1. The fact that this is coming in and this is coming out, I would basically just kind of free body diagram this.
Right.
As that is P2A2. That's P1A1, which means that's going to be 50. And that's going to be 2.
Yeah. And that's it.
So that means that, so that's the pressure from this. Okay. So that means that to sum my forces in X, I would have, that's positive 50. Plus, we're just going to call this plus because, now I'm calling this plus not because it's going in, but because if we're assuming that's positive X, so then I would have plus 2 times cosine of, let's just call that 45 degrees.
Yeah. And then you'd have your,
plus my Fx.
right.
And those equal 0.
No, wait a minute, they don't equal 0.
Okay.
They equal to the right-hand side, the sum. They equal this term right here. They equal to that right there.
Okay. Okay, so
And that's
then
the
what I
key.
need to figure out is how do I get this then? So
Okay,
that
well,
is, okay.
Yeah, and
Because
so
that would be, if that doesn't equal 0, that's why I keep not getting the right answer.
yeah.
Because
So
I'm doing basic.
okay, so
math.
what it's doing is just like I was saying. If you look at this thing, you're taking the Vx
right
at the entrance and the exit times essentially what appears to be the m dot.
Okay, so this side of the equation then, and so this part I would get from here.
Right, exactly.
This part I would get just from converting that to a
Right,
free body
exactly.
diagram with these pressures.
That's exactly
Okay,
right.
now that is dx times rho. We're just gonna, let's just say rho is 1 for now.
Yeah.
So that would be, let's say that's V1 and that's V2.
Yeah.
So then that would be the sums of the Vx values. And
And this.
all right, rho is, if we say rho is 1, so that would be, that V bar is what? Is that just
That's
the
a
direction?
velocity. That is the velocity vector dotted with the normal.
Okay,
So that's the
this
plus being out and in being negative.
Okay, so these two together become just +1 or -1.
Yeah, well,
Okay.
they become plus V or minus V,
Plus V or minus V.
right? So what you
Okay.
get is rho VA, either a plus
Or a minus.
or a minus, and that's
And
it.
it's plus if they're the same. So this term would become
Negative,
negative rho V1 A1.
right?
Okay.
And then that one
And
would
then this
be
one would be positive rho
V2A,
V2A2.
right?
Okay. Okay. A2. And then
And then you got the VX.
Where,
So-
how do I get the VX?
Well, the VX is the X component of the velocity, where is what you'll see.
So in
The
this
X component here
case,
is just V1.
So if you get the right-hand side, this becomes negative rho V1 A1 V1's X component,
Yeah, which is just
which is
V1.
just negative rho V1 squared A1.
Right.
And then over here,
See, now you've got a negative component.
right, so this would be positive rho V2A2 times, because it's negative, negative V2 cosine of 45 degrees.
Right, that's it.
Okay, which means negative times negative means that becomes
The whole thing.
negative
Yeah.
rho V2 squared A2
And then your cosine.
cosine of 40 degrees.
So now
this
what you
entire
do,
left
you take this one
side,
and that one and put them
and
both
this goes-
together over
okay.
here. And that's
So
it.
Negative rho V1 squared A1 minus rho V2 squared A2 cosine of 45.
Yep.
And then for basically whichever one of these things it tells me I don't know, I just solve that.
Solve it. That's it.
Okay.
That's all there is to it. And then doing the two diagrams is a good way to do it because you split the thing.
Okay. So basically
Here, I'm gonna go ahead and cut off my machine.
P1 A1 plus P2 A2 plus F of the anchor